Hello, welcome to Houdini 19 real-time Pyro workflows, chasing photorealism. My name is Mai Ao. I'm a technical artist at SideFX Labs. I'm very happy to be here today to share with you new techniques and solutions we're bringing you in Houdini 19 to help you achieve beautiful and memorable Pyro effects in your real-time engines. As a quick overview, this is what we're going to be talking about today. We'll start off as a mission statement, what we're trying to achieve. Then we'll move on to a quick start and talk about our new viewport rendering techniques, ACES color spaces, how to generate Flipbooks. We'll also do a deep dive into different texture maps and the updates we've made to them. Let's include base color, smoke color, motion vector, normal, what I call MDC. I'll explain that later. Depth, and we'll talk about the real-time shading aspect of it, the dynamic controls you will have in engine. We'll finish off talking about a rather experimental feature, what I call volume photogrammetry. But before that, I would like to give a special thanks to my colleague and friend Attila and Omar. They've been instrumental on the R&D side in building the Pyro techniques in our Houdini main, and they helped me a lot in finishing up the real-time pipeline, bringing the two together, and hope you guys will enjoy it. So first off, what are we trying to do? I've been working in production before, and Pyro is one of the effects aspect that I'm really passionate about. So nowadays, the advancements we've made in real-time environment and characters are incredible. One thing I'm starting to notice is some of the effects, such as smoke or fire, when put in contrast with the hyper-realistic environment, they start to look a little bit gamey due to possibly no resolution, or the lighting just seems a bit off compared to the environment. So that's something I really wanted to tackle on the real-time side and bring together Houdini's simulation and rendering power with what we can do in engine. So that's our first objective. The second one is that I wanted to create a really no stress workflows for you guys, because there are so many small steps in this process. You need to worry about things like, what color space do I use? Do I set my PNG to be pre-multiplied or unpre-multiplied? All kinds of lighting setups, shader tricks, and all that stuff. What I wanted to do is to standardize the workflow so you don't have to worry about all these technical details that might be unnecessary to being creative, and really that you focus on directing the best visual results you can get. But before we can do that, we can't just imagine things of what should be called realistic. If we want to make realistic stuff, we started off with comparing against the photographs and see what are the elements that differentiate them from real-time rendering, at least currently as they stand. So some of the things I've started to notice is that the smoke and fire, they're really blending with the environment a lot more in photographs because of the lighting they pick up from the sky, for instance. And depends on where the dominant light, such as the sun, coming from, the shading will be different. The other aspect of it is how dense the smoke is. In this example, the pyroclastic volcanic smoke, you can see a lot of surface details. That's also possibly due to the scale of it. Whereas for something small and soft, you see the light penetrate in a much softer and gentle way. Another interesting thing about fire is that you will see dark areas in front of them, bright areas that mask out the emissive components. You will also see, even with this fiery situation, you will see smokes on top of it that's still picking up some of the environment light, so it's like tinted blue. So with these in mind, this is our attempt at bringing the gap between video games in the top left and bottom right closer to the photographs in these two as a reference. I think we're getting close. I'm pretty optimistic about the results, but of course it will only get better from here. So this is things in motion, captured in Unreal Engine 5. This is a Pyro effect rendered out on a card. So let's dive in and break down the individual components that made this effect possible. So for quick start, now the process of getting your Pyro started is made ever simpler. So you can go to the shelf tool, and then under either Pyro effects or simple effects, you can click on these tools. They'll drop down preset for you, from which you can configure and suit your own visual needs. So one thing to note about the simple effects is that they will drop down sub level, in other words, geometry level nodes, like this Pyro solver over here. It's no longer dynamic Docker network node, which might be a bit more challenging or difficult for new users. So this is part of our overall effort to bring more things into subs and unify them over there and make the workflow simpler. So on this Pyro solver, you have the option to choose what simulation type you use. You could use sparse, or you could use minimal OpenCL, which leverage the power of GPU to make your simulation much faster. We'll also drop down the Pyro bake volume, which process the result of the simulation. And this is our secret weapon in making the Pyro look really, really sexy in the viewport. So here's the process in action. As you can see here, I just simply click on the tab and control click on one of the shelf tools, and it will drop down a network in the world origin. Have some of the things already preset for you. Then you can configure from here. One thing I really want to highlight is our viewport rendering, which is looking really good in Houdini 19. So here's one example. This is Flipbook directly from the viewport, an animated source minimum solver Pyro effect. The animated source is referring to the tip of the torch being animated along with the character, and the minimum solver took care of the rest. So here's another example of a very beautiful torus effect. It just shows you just how detailed and amazing it can look already without offline renderers. This is directly from the viewport as well. So you can flip with this, you can put this in your game, and it would just look as good. One secret source behind the amazing colors is the adoption of Aces color space. So this is known to some people, but would like to make it more popular, especially when you're working Pyro effects. So ACES stands for Academy Color Encoding System. It's popular in the film industry, but the game industry can also benefit from it. Here's a comparison. On the left side, we have the standard sRGB, and on the right side, we have the ACES sRGB. As you can see, the difference is quite drastic, and the right side looks much better. The process to configure and set up ACES colors is a little bit convoluted. That's why we're aiming to provide you with tools, tutorials, and documentations of how to set it up. Next, we want to introduce you to the new Flipbook generation methods we have. Previously, we have a Flipbook generation methods in SideFX Labs, but now we have more. Now you can directly do this in the bottom left of your screen and do the Flipbook render. On the size tab of the render Flipbook settings, there's a new option called sheet size. This will allow you to specify the row number and column number of the Flipbook you want. So once you hit render, what's going to happen is that it will render out every frame and automatically composite every frame into the grid that you see on the right. Additional benefit of this is that you don't have to save out the intermediary files and load them to composite them. What happens under the hood is that once every frame is rendered, it's copied to the destination buffer so that it's more memory efficient, it's faster. Then you will get is a single frame in the end play that is the ready-made Flipbook. If you don't want to do it manually, we also have a more automated process in the form of a tool that Labs will be offering called Flipbook Textures. So what this tool does is not only composite and render the textures, it also gives you the option to render out different types of textures and configure the settings along the way so that the process is really streamlined. You can click a few buttons and everything should be ready to go. Now let's dive into the different textures that we offer. So the first one is base color and smoke color. On the left, you see the base color, and on the right is the smoke color. The difference between the two is the smoke color is basically base color minus the emissive component of it. This workflow is different from the previous workflow of using an emissive map, which describes the emissive component by itself. How we derive the emissive component now is that we simply subtract the base color by the smoke color. The advantage of using this kind of approach is twofold. One is that by definition, because it's a subtraction, it very nicely isolates the emissive components without changing the black masking part on top of the volume that you saw previously in the photographs. So as you can see here, if we don't turn on the emissive and just plug in the texture into base color, you get the dark version like this. Then you can independently control the intensity and the curve of the emissive component of it, like the fire. The second benefit is that we can use the smoke color by itself as a source of doing non-directional scattering. This refers to the color the smoke will pick up from the sky or the general environment. Because it's rather like omnidirectional, the smoke color has the ambient occlusion baked into it. So it's not just a straight up everything brightens by the same amount of values, but it brightens with a gradient, make it looking really good like this. Next, we want to talk about the new in-viewport motion vector map and the new encoding that we're going to be providing. So motion vector maps used to be rendered using Mantra, which is considerably more slower. Nowadays, with a simple node, you can turn the viewport into the motion vector view, as well as normal view, which we'll talk about in just a bit. So the benefit of this is that you can interact with it. You can rotate your viewport, you can change the camera, and the motion vectors was always computed in relation to the angle you're viewing at and the size of your viewport. So on the left side, we have a snapshot of what one frame of motion vectors might look like. On the right side is the encoded version, which looks kind of funny, but it provides better accuracy using a small amount of memory. Here's a comparison to show what the encoding is really doing. So in the center is the expensive version, which we're using as benchmark of 16-bit per channel motion vectors. So you can see everything is smooth and there's not much banding. What you will see on the left side, which is standard RA, GA motion vectors, you can notice the banding and it looks very sort of pixelated. We changed basically how we do the encoding, and on the right side you see the new version, which is, so what you see here is the decoded format inside the Unreal Engine viewport. So it's different from the texture you saw before. As you can see, it's much closer to the 16-bit version and much less banding compared to the 8-bit version. What this will mean is that if you have serious banding, some pixels that should be moving at different speed will end up moving with the same speed. So it makes it more jittery and not smooth. So that's the problem we're trying to solve while keeping the memory size down. So here's a result of what it looks like. First, it's no motion vectors. It looks very jumpy. Then it turns into this smooth result. In addition to motion vectors, we also have the new viewport normal map, which is sort of a new interpretation of how we do normal map. So on the left side is a normal map rendering from the viewport. And at the end, this is something you can interact with. You can rotate the volume, you can change the camera position, and the normal map is always computed in relation to the viewport. At the right side, what you see is a grayscale, which is showing one of the components. Because normal map, we can actually throw away one of the components. We can just export two texture channels and derive the third component dynamically in the shader. This saves more texture space and allow us to pack the normal map into the same texture that we put the motion vectors. Another change we made is that this normal map allows us to have more detailed and accurate per voxel normal. So in situations like the pyroclastic volcanic smoke, as we've seen before, you'll be able to reflect those fine details. Some of the earlier way of doing normal map is to use RGB lighting rig that coming from 6 directions, and then reinterpret the result of that light into a normal. That creates a more smooth normal overall, but it has to, so that version has to blend with the more like per voxel detail level. And because each pixel you end up only having one option to like encode one color, so the blend always like sacrifice one or the other. So in this way, we'll preserve this highly detailed version, and we're going to do the high level normal in a totally different way that will have more accurate lighting results. So here's a result of having no normal and normal. When I turn the toggle on, that's when we have normal. When I turn the toggle off, it's flat. So the new lighting technique I mentioned previously is what I'm calling the MDC, the multi-directional contribution map. The name reflects what it does. It really is a calculation of light coming from different directions and how much each direction should contribute. So these maps allow you to dynamically interpret your lighting direction in the shader. So you could change your lighting direction to anywhere you want, and that should light them, relight the smoke properly. So on the left side is one single channel of one of the lighting directions. As you can see here, it really captures that the backlit look of the smoke when the light is coming from the back. And on the right side is several different channels composited together, and each channel occupy its own color. That's why it looks kind of confetti look, but the data is separate. So this rig uses an octahedron, and the lighting direction basically comes from the face normals of the octahedron. So this overall provides a much better coverage of different angles, because interpreting light directions between angles is usually kind of problematic. So having a better coverage, reduced angles between different light in the rig, make the overall result much better. And the position of light is also important. We position the light in a way that's much closer to where you might actually be lighting your smoke from. You would rarely ever light your smoke dead on, or straight from the back, or straight from the left and right. So all these techniques combined together give you a texture map that could provide a much more accurate result when we put it in action. So here's it in the shader. What I'm doing here is turning on the result of the MDC maps. So the parameters I'm calling here is directional scattering, because it has a strong direction here. It gives the rim light because the light in this instance coming from the left back. And this is what it looks like when I animate the light source. It does one cycle in front of the smoke and another cycle at the back. In the front, it looks kind of weird in this instance because the light in the environment is coming from the back, which kind of highlights the importance of having the light in your shader match the light in the environment. As you can see, you get smooth transition as the light rotates in a circle. All this is coming from the MDC map. This is a much better result compared to normal maps. Normal maps, at least the standard workflow, will not give you this kind of fidelity. Next, we'll talk about the normalized depth map. What this does is that, based on the camera, it computes a depth map that starts with the voxel closest to the camera and ends with the voxel that's farthest away from the camera. They normalize the range into a 0 to 1 range. So it doesn't matter how big your smoke actually is in Houdini, because you need to dynamically interpret that anyway in the shader. So we just output a 0 to 1, which makes it also easier to export. You can just do like a one channel compression in the engine without using like too much texture memory. Now this is put into use. Here the fire is originally on a card, but as you can see, it gives you this illusion that the fire is dancing around the skeleton and the chair, and it's intersecting the chair at a different depth. But actually, the geometry itself is intercepting the chair at the same depth. As you can see, it's quite effective. Here's another example in the plane. You can see when we turn off the depth, the card just appears to float in front of the plane. But if we turn it on, you can see the smoke appearing is surrounding the plane as expected. This is everything put together as we talked about before. Turning on normal, motion vectors, turning on the emissive, turning on the MDC maps, give it a nice rim light, and the omnidirectional light that's comes with a tint of the sky color. What I'm doing here is to changing the relative light position, and see how the smoke react to that. This is everything without all the features, and playing backwards with everything turned on. Now, volume photogrammetry. It's an experimental feature I've been working on. So, say we have an example like this in Houdini, which is showcasing our newest and super cool volume deform SOP. So what this is doing is that it took a straight upward simulation of a fine tornado and bend it. So you can do same simulation and bend it differently and produce different results. Now, if you want to render this onto a card, you basically get the same visual look in the shader if you just tweak a few parameters. But the question is, how do you make it so that you can work around it and look at the same thing from different angles? So the current existing solutions is a little bit tricky. It either uses a lot of texture memory if you want to do volume texture. Volume texture also, because you have to do the trade-off between texture memory and resolution, you also sometimes end up with a relatively low resolution. So it looks, the smoke will look kind of smooth. The other option sounds probably even more crazy, is to do the imposter textures, which is sort of like the dynamic texture that can be viewed from different angles, but ultimately rendered on the card. The thing about imposter textures is that it's cheap if it's just non-animated geometry, but when you have time dimension, that just multiply the texture into way too much for you to afford. So I've been looking for sort of the trade-off between these, and what I'm coming up with is like using a metaphorical photogrammetry. It's not really photogrammetry, but the idea here is to take photos of the simulation as you would, basically generate a bunch of rendered images. Then we'll try to reproject the images onto a geometry that's converted from the volume surface. So what you see here, the picture is colored by the NDC coordinates values. The NDC is the normalized device coordinates. In other words, it's similar to like the screen space coordinates. So here you can see that it's reacting to every aspect of the camera settings, like including its clipping panes, including the camera position, photo lens, and everything. So what happens is basically once you have rendered out the images, you compare that against the texture space that's unwrapped from the geometry. So if you have a point in the texture, you can query and find out where that point corresponds to in 3D space. And based on the 3D space, you can compare that against the camera you used to render that texture frame. Then you find out where should that point appear on your texture and what's the UV coordinates over there. Then you can go and fetch the color at that UV coordinates and put it back all the way onto the texture space. Then you end up with this look. Here's more of an example. So on the left, you see a different camera angles capturing the same fine tornado. Then in the center, it's that image transferred through the process I described earlier, from texture space to 3D space, then back to the camera space of the cameras that capture the particular frame, and add everything together, average them. You end up with the same textures now be able to transfer to the surface of the geometry. It doesn't matter like what's the aspect ratio of the cameras you're capturing with. As you can see, the top down views at the bottom left, they are using like a square frame, but the top left 2 is more like a slender frame that doesn't affect the result. So on the right side is everything put together. You basically have the look of the pyro smoke on the surface of the geometry. Here's a test example of our little piggy. So on the left, the texture of the piggy actually comes from different photographs, quote unquote, that is taken from different directions and composited together and reprojected into the texture space. On the right is the original texture that the piggy has. As you can see, the result is very similar when we're dealing with this kind of geometry, like hard surface geometry. With smoke, it's a bit trickier because it's hard for different camera angles to agree what is the surface of the smoke, because the smoke doesn't have very solid definition of what the surface is. So you will inevitably, at least currently, look a bit more blurred out, because if you don't blur the results, you might end up with different results from different cams, causing an edge between them. But here's a prototype. A little bit rough, a little bit rough on the edges, because it's just more like a tech demo than a beauty artistic demo. So it's the same simulation of the fire tornado I showed earlier. In the center is more closer to the original color. As you can see, the key thing here is that geometry, the animation of the geometry and the animation of the textures are in sync together. Like you can see the flame flowing in the same way as the geometry is deforming. So that's really the key aspect of it and the things that I wanted to achieve. You could add a bit more particle system around it to make it more immersive. On the left and on the right is different shading. Left is more of a translucent, I think it's additive in this case, with some kind of depth blending. On the right, it's still opaque, but it's we just change the hue to create this sort of fell magic look. So just to reiterate, the animation of the look on the surface is a flipbook. And that flipbook means like every frame of the flipbook is a look of the UV map. And the textures contain the color of what the UV map should have. So when you play the UV map as a flipbook, it's not a traditional flipbook where it comes from a camera perspective. You're playing the flipbook on the surface of the geometry. And even though the flipbook itself might look kind of crazy, but when you stitch it together, it looks very smooth and seamless, especially in motion. If you pause it and like closely examine it, it might not be as seamless as you would hope currently, but hopefully it would get better. So here is a brief recap of what we talked about. A lot of the hard work from the Houdini main side is done by my colleagues, so I can praise them and say it's stunning details and colors straight from the H19 viewport. On my side, what I worked on is the new solutions for real-time volume reshading. So you can have robust controls in the shader to make your volume look fantastic. And we worked on creating like low stress workflows, so you don't have to worry about different settings. We'll set it for you. Then we ended with an experimental volume photogrammetry feature. Hopefully it will be more mature in the near future. As for near future, what we'll end up making depends on what you guys need and what you tell us. So please give us feedback and what you think is missing or what you think we can improve. We really appreciate that. And thanks for watching.